In 1843, British professor Edward Forbes proposed a radical new hypothesis on deep-sea life. There wasn't any. Forbes had been dredging the Aegean Sea and cataloging the species that were dragged up. And he saw a pretty clear pattern. The deeper his ship dredged, the less it collected. So he figured that below about 300 fathoms, roughly 550 meters, the sea was entirely azoic, or lifeless, because of its harsh conditions. And for decades, this hypothesis was widely accepted by the scientific community, despite it being deeply wrong. And today we know that the dark and murky depths are home to many species, from invertebrates to anglerfish to lanternfish and snailfish, to name a few. But in a sense, Forbes was accidentally kinda onto something. See, those weird deep-sea fish may look ancient, as if they've been lurking in the abyss since the beginning of time, but in reality, they only just got down there. Despite starting out in the water, the fossil record suggests that vertebrates conquered both the land and the air before they conquered the depths. So what took them so long? Well, what made it possible for fish to finally colonize the deep sea may have been flowers. The deep ocean is the single largest habitat on Earth, but the fossil record suggests that for most of the history of complex life, vertebrates just didn't go down there. The earliest vertebrates emerged in the shallow waters of the Cambrian period, over 500 million years ago. And by 375 million years ago, in the Devonian period, some had begun to crawl out of the water onto land. By a little over 200 million years ago, in the Triassic period, some of their descendants even developed powered flight and took to the skies too. Yet through all that time, while some vertebrates were on epic evolutionary journeys from the water to the land and into the air, none seem to have just swum downwards. There might be some evidence that fish were adapted for deep-sea living in the late Cretaceous period, but we don't see any definitive body fossils of fish down there until roughly 50 million years ago, in the Paleogene period. Plus, the genetics of the fish that dominate deep-sea ecosystems today also show evidence of this delay. Molecular clock data suggests that most modern major deep-sea fish lineages, which are part of a larger group called the Neoteleosts, only arose during or after the Cretaceous. Was it really quicker and easier for shallow water fish to evolve into dinosaurs or pterosaurs than just evolve into deep water fish? There are even secondarily aquatic vertebrates older than this, fish that left the water, evolved into land animals for a while, and then returned to the water, all in less time than it apparently took for deep-sea fish to evolve. This mysterious lack of evidence of deep-sea fish for most of the history of life is one of the largest gaps in vertebrate evolution. And the simplest hypothesis that has historically been proposed is that the gap is real. There really was no vertebrate life in the deep sea before the Cretaceous period. But why such a long delay? Well, it's easy to imagine why vertebrates might not have been in much of a rush to colonize such a harsh and resource-scarce environment. Beyond about 200 meters down, which is where the deep sea technically begins, there's so little sunlight that photosynthesis becomes basically impossible. Now, photosynthesis is usually the base of most ecosystems. Without it, deep-sea food webs have to rely on much worse sources of energy, like detritus that gradually sinks into the depths from above, and what's called marine snow, which deep-sea species can scavenge for food. Or chemical energy from deep-sea vents and seeps, which some microbes can harness to form the base of food webs. And the deeper you go, the harder things get. Thousands of meters down, for example, there's crushing pressure and extreme cold and constant darkness. And it might have simply taken a long time for the right mutations and selective pressures to come together to make the transition possible for vertebrate life. But not everyone thinks that the delay was simply about the challenges of adapting to harsh conditions. Because it's still kind of strange that it took so long for shallow water fish to conquer the deep. There are also a bunch of major challenges too, and drastic adaptations required for moving onto land and into the air. Yet vertebrates still managed that much faster than moving into the deep sea. A fish evolving to stroll around on land is no walk in the park either. Okay, well, technically yes, that's exactly what it is, but you get what I mean. Plus, invertebrates seem to have made it down there without such a long delay. Another hypothesis suggests vertebrates actually did make earlier attempts to reach the depths, and the delay we see in the fossil record isn't the real story at all. See, the deep sea is prone to periods of anoxia, the loss of oxygen due to changes in ocean circulation. And there's been a series of known major global anoxic events in the planet's history that could have wiped out older deep-sea vertebrate ecosystems. So perhaps modern deep-sea fish represent just the latest recolonization that started in the Cretaceous, after the last global anoxic event around 94 million years ago, and we're missing the fossil evidence of those earlier species. And that lack of fossils would make sense, seeing as the oceanic crust is constantly recycled in a tectonic process known as subduction, gradually destroying the fossils that do form down there. Which potentially means that today's deep-sea fish might be only the latest iteration in a long but hidden cycle of extinction and recolonization stretching back hundreds of millions of years. In 2023, though, researchers published a study that added a whole new dimension to the debate: the oldest fossil evidence of deep-sea vertebrates ever found. The fossils came from the Apennine Mountains of Italy and date back 130 million years ago to the early Cretaceous, when this region formed the bottom of the ancient Tethys Sea. They weren't body fossils of deep-sea fish themselves, but trace fossils of at least 3 distinct species moving across the seafloor. These included a wave-shaped trail where a fish had been dragging its lower fins across the sediment as it went. But the more numerous fossils were of long rake-like scratches and small bowl-shaped pits. Both of these are virtually identical to the marks left by some deep-sea fish today when foraging for small invertebrates buried in the sediment. And the feeding pits in particular suggested to the researchers that the fish responsible for these trace fossils weren't the remnants of an ancient deep-sea vertebrate ecosystem, but the pioneers of our modern one. Because those pits required a highly developed suction feeding apparatus, characteristic of the modern family of fish that dominate the deep sea today, the neoteleosts. So the trace fossils may represent a very early stage of the neoteleost diversification into the deep sea that continues to this day. While this doesn't rule out the possibility of earlier waves of deep sea colonization by older lineages that we haven't found fossil evidence of yet, it does suggest what the trigger for the latest colonization might have been. Because right around 130 million years ago, when those trace fossils date back to, the deep sea was changing due to the ripple effect of a revolution unfolding on land. See, flowering plants, aka angiosperms, also emerged in the fossil record around this time and took over the world over the course of the Cretaceous. And the researchers argued that as they radiated and spread, flowering plants would have increased the amount of organic matter finding its way into the oceans. The nutrient-rich runoff in turn would have then increased the productivity of the marine realm, including causing blooms of phytoplankton at the surface. And some of this extra organic matter would have eventually found its way into the deep sea, raining down as the marine snow we mentioned earlier. This sudden extra input of energy into the deep sea meant that food webs down there could support a greater abundance and diversity of invertebrates, and we see the diversity of their fossil burrows increase around this time. And for vertebrates that could use their mouths to get those invertebrates out of those burrows, like the early deep sea neoteleosts, transitioning to the abyss finally became worth it. So maybe what eventually ended the deep sea fish delay was an ecological domino effect that began with flowering plants taking root on land. We still have a lot to learn about the natural history of the deep sea, the largest and most mysterious part of our planet. But if it's correct, this new hypothesis shows that nature isn't a collection of neatly separated ecosystems. Everything is connected, no matter how remote, from forest to seafloors and from flowers to fish. And far from being lifeless, like Forbes thought, the deep sea just needed a new group of plants basking in the light to give rise to new animals that lurk in the darkness. Want to know more about the Cretaceous anoxic event? Check out our episode, That Time the Ocean Lost Almost All Its Oxygen. And deepest gratitude to this month's Eontologists. Addie, Annie and Eric Higgins, Carl Wolfel, Jackie Scott Ralston, Jake Hart, John Davidson Ing, Juan M., Melanie Lamb Carneville, Nico Robin, Raphael Haas, Tony Dye, and Steve. By becoming an Eonite at patreon.com/eons, you can get fun perks, like getting your name in the description and helping bring back Steve. And as always, thanks for joining me in the Annie and Eric Higgins studio. Subscribe at youtube.com/eons for more primordial ordeals. Also, I don't know if it's still rolling, you can't see how cool my earrings are, but my earrings are very cool for this episode. Please admire.
They are very good.
Thank you. Like detritus that gradually sinks into the depths from above. I don't like any kind of seafood, so don't give me detritus seafood too.
Seattle!
I know.
So jealous.
Yeah, I eat the ferns instead.